Alright, this is precalc chapter 8.2. What we're going to do is we're going to talk about vectors in the coordinate plane. Now in 8.1, if you remember, we had to worry about a direction, a magnitude, and they could be kind of anywhere as long as, we had a direction, a magnitude. Sometimes we had to take a protractor, we had to take a ruler. It made our lives a lot easier to figure those out. Well, really, to be honest, not very convenient. I even had you guys kind of make your own scales, your own lines, saying, hey, general direction, put a scale to it saying that is the size of 10 or 15. So there's got to be a better way, something we can do more algebraically here. And so the idea is, let's break it down to something we really know. We really know how to do things in the coordinate plane. And so what we're going to do here is we are going to take vectors, which has that magnitude and it has the direction, and kind of superimpose it onto the coordinate plane, which will allow us then to be able to use it more user-friendly. We don't always have to have the protractor and the calculator and ruler with us. We can start to deal with it with the coordinates. So basically, if I took something from standard position, which is the origin here, and I plotted a point, the arrow, or say the vector from 0, 0 to xy would actually be just xy. I'm going to show you that in the next slide here. And so here we're going with vector AB. So if I wanted to, I could denote vector AB. That's still the same from last time. But the cool thing about it is that it gives us a vector. And this vector uses a little bit different notation than, say, parentheses. It uses kind of like a less than and greater than symbols to denote this. x2 minus x1, comma y2 minus y1, with another one of the, with this one, a greater than symbol type on the ends. Those symbols here at the end will denote that it's a vector instead of just a point. And it's based off of this, guys. It's based off the fact that this is x1, y1, this is x2, y2, and if I wanted to find the distance, right, distance, from point 1 to point 2 in the x direction, it's the difference in the x's, the difference in the y's for vertical, and that, remember, is talking about those component forms we kind of broke down yesterday, where we found the side lengths. And we actually used sine Sokotowa for that. This time, we're going to use the points to find that. And so, first up is just stating a vector in component form. Here's the thing. Because this is in this form where I take the second point and minus the first point, that means I can take this vector, and it does not have to be at 0, 0 start. If it's at 0, 0 start going to the point, then this point is your vector. Because anything minus 0 is that thing. Makes it a lot easier. But equivalent vectors have the same direction and they have the same magnitude. And so if I move over, up and over, or over and up, the same, I will have the same direction, I'll have the same length, therefore same magnitude. So first up is I have these two sets of points, and I want us to find the vector of these points. Okay? Now we're all going to assume that A to B. So remember, vectors are different. If I went from vector A to B, it is different from vector B back to A. And so if I want to know vector A, B, so I'll put vector notation there, all I am going to do is take B, which is 0.2, minus 0.1. So now this time it does matter. It does matter which one I call 0.2, which one I call 0.1. It's always final minus initial. Final minus initial, okay guys? So this would be 6 minus negative 2, comma, 1 minus negative 7. Don't forget your vector notation there. But then remember, we subtract a negative, we are adding, so this becomes 8, 8. So there is your vector. I am going over 8 and up 8. Hence, actually, everyone should know that if I had equal sides of a triangle, this actually would be a very special triangle. It's a 45-45, so we would actually have an angle. And later on, you can find the hypotenuse, aka the magnitude. That's the next slide. It could be as easy as that, guys. And that's, the first section of your homework is just creating these things. So, next one, let's do vector AB again. I want you guys to think of this one on your own first. I am not going to pause the video. I want you guys to try this. I'm going to stay quiet for 10 seconds. Okay, that was about 10 seconds there. So remember, final minus initial, and therefore I have negative 9 minus 0, that's a nice one, and negative 3 minus 8. And that's negative 9, comma, negative 11. So if you got that, awesome. If you didn't, did you do final minus initial or the B minus the A? That is the biggest thing that we have to remember on that one. So, moving on. As I said before, we got to have that magnitude. We got our sides. So therefore, if I have sides of my triangle here, why can't I find the length? The length of the vector, remember, is the magnitude. Just why did we have you guys measure it back in 8.1? Because that was a length. Magnitude. Guess what? If this is my triangle, just like before, I can call this A, I can call this B. I have the difference in the x's, the difference in the y's. That's like A, that's like B. Wait a minute, it's a right triangle. A squared plus B squared is equal to C squared. But I'm solving for C, or in this case V, so I have to take the square root. Notation though. Notation is they take the absolute value of a vector. Now, maybe I should put this into more bold font, right? Because I don't have any other notation on there. That is vector V. So, the absolute value of vector V is really talking about the magnitude of vector V. And that is just the difference squared plus the difference of the y's squared. Add them together, square root, and you got it. Now here's the cool thing. That's if I give you a set of points, find it. What happens if you already have it converted into component form? Whoops. If I already have it in component form, that is A comma B. Cool thing is that A is the difference, B was already the difference, so therefore it just becomes the square root of A squared plus B squared. So I'll let that soak in there for a second. These are not too bad. I think this is easier than what we were doing yesterday. Okay, moving on. So I want you guys to find the magnitude of AB. I do have both of these in rectangular form, right? So we have to put it into component form. So we're going to do it the two different ways. We'll straight up, we're going to use the points in the formula. So in this case, I want the absolute value of vector AB. And so we could go through the whole process. It's the square root of 6 minus a negative 2 squared plus 1 minus a negative 7 squared. Or wait a minute, that was what we did earlier, and that is the square root of 8 squared plus 8 squared, which is 64 plus 64 square root, or the square root of 128. So it's not too bad. I don't think the square root of 128 turns out to be a nice number, but it's about 11.3 if I had to use it to graph or use it for some other calculations, or they want to one decimal place. But square root of 128, make sure you always simplify your square roots where you can, and where you can't, you leave it as a square root for the exact answers, or to one or two decimal places when asked. So hopefully that was pretty straightforward. The next one, what I want to do is I actually want us to convert this to component form first, kind of showing that as a vector form, and then we'll use the formula. Now wait a minute, don't those numbers look really close to the one we just did? It does, but it should be negative 9 minus 0, comma, negative 3 minus 8, which is negative 9, comma, negative 11. And now all I have to do is take the square root of negative 9 squared plus negative 11, it's a plus, squared, which is 81 plus 121 with the square root, which equals a square root of 202, or approximately 14.2. Both times, it's not too bad. I know I'm moving pretty quick, but I think most of us would be like, okay, I've done this before. I've seen these pieces. I've dealt with this stuff. I can make this work. The biggest thing is to remember is that now we're talking about vectors. You got to use the proper notation, and the fact that the magnitude is the length of your vector, or just the hypotenuse of your triangle. And I think that's pretty cool. Okay, this one, I already have it all spelled out for you, so I'm going to keep talking now. Is that these are vector operations. Here's the cool thing. If I'm given 1, 2, 3, 10, 20,000 vectors, and I want to add them or subtract them, and multiply a scalar, as you can see here. Remember, it's a scalar multiplication. It is not vector multiplication. We'll get to that later on. So, if I'm given vector A, and I'm going to denote vector A as A1, A2, B can be B1, B2, those are vectors. And I'm going to let K be a scalar number. Just 2, 3, 8. I don't care what it is. We can deal with that really simply. It's easy. You guys are going to like this. Basically, if you're adding vectors, you add their components. So look what happens here. Vector addition. If I want to add A plus B, I add A1 plus B1, comma, A2 plus B2. I add the x's, we'll call x's, I'm doing quotations in the air you can't see, and then I add the y parts. That's it. So if I was adding 3 vectors, I'd add all 3 of the x's, all 3 of the y's. Boom, you got it. If I am doing vector subtraction, the first vector minus the second vector, it's just the first point of A, the first x minus the second x. The first y minus the second y. In this case, A1 minus B1, A2 minus B2. So hopefully you guys are liking those. And then the last one we're going to talk about is scalar multiplication. When I multiply a vector by a single number. That is very important. I'm not taking vector A times vector B. That's something different. It has different operations. But when I multiply a vector by a constant, a scalar, I multiply each component by that component. Or by that scalar, sorry, that should be another comma in there. So this would be Ka1 times, comma, Ka2. And I think that's going to be really simple for today. And now we have to is do a couple examples of this. So 2 more examples, and then you guys are going to be given your homework. So here we go. First up, I'm giving you 3 vectors I see. I eliminated one of the examples, so if you really felt like you needed to do it, you could. The last example does bring in z and just has you do more things. But these first two is going to be just good enough, or good enough, not say just good enough for you guys to understand everything needs to do. So vector w there is -4, 1, y is 2, 5, and z, which we are using. So actually we're not using the y. And that will be -3, 0. That is a -3. I'll fix this for us here. I don't like that. So -3, 0. As we can see that a little bit better now. So the cool thing is, I want to do 4 times w plus z. Order of operations still applies here. I got 4 times w, vector w, and then I got plus z. That means I need to do the multiplication stuff first. I need to do 4 times w, then I can do plus z. I am going to show L of my work. I am going to show it's 4 times -4, 1 plus, look at this, I'm just placing the vector in its spot where it should be. It's in the component form. And then I'm going to, in the next step, do the multiplication. I'm going to bring the the 4 to the -4 and the 4 to the 1. So I can even do this. It's -16, 4. This vector is now 4 times the length. Now, if I was starting at 0, 0, which I don't have to, I would go backwards 16 and then up 4. So it kind of looks like a north, I'm going to say like a 65, 70 degrees west, because it should be more of it this way, right? It's going to be longer or closer to the horizontal than it is going to be up. That line even looks kind of bad, I think, on there. Be more like this. Not needed. You don't have to draw that, but can you guys picture that I'm going backwards really far and then going up only a little bit? And then I'm still adding the vector -3, 0, which would result in a vector of -16 plus -3 and 4 plus 0, or -19, 4. And the cool thing is, after this, I could ask you for the magnitude of that. That's -19 squared plus 4 squared. Add them together, square root, boom, you got it. Probably have to use a calculator to get to a decimal or so. And if I have -3 times w, then it's just -3 times -4, 1, which is 12, -3. And I think that's pretty easy. So I'm hoping you guys liked it today. That's the first day. Tomorrow we are going to go into unit vectors, and then we're going to be able to find some components, and we're going to bring in I-hats, J, or I's and J's. We used to call them I-hats and J-hats last year. And we're going to bring back a little cosine and cosine things. So it's going to be a little bit more interesting. Hang tight on that one. So your homework then at 8.2 day 1 is page 497, 1 through 17 odds. Make sure on 1 through the 9 there that you make sure you're reading the directions. I want it in component form and the magnitude of that vector A, B, given the initial and terminal points. So therefore, do two things. Put it in component form and find the magnitude. So it's basically just a continuation straight through there. And then on 11 through 17, you will use the vectors just like our last problems and combine them. Make sure you do your scalar multiplications first before you do any additions. Alright, I hope to see you guys soon. Have a great day.